principles shown by this toy gyroscope play an important role in modern flight instruments. During our last program, we introduced the flight instruments and examined those which respond to the pitot-static system. On today's program, we'll discuss those that operate on gyroscopic principles. These include the attitude indicator, turn coordinator, and heading indicator. We'll also take a close look at two self-contained flight instruments, the magnetic compass and the outside air temperature gauge. And we'll take a brief look at the remainder of the instrument panel. First, let's look at the gyroscope. Basically, a gyroscope is a mass spinning rapidly about an axis. Any spinning object exhibits gyroscopic properties. However, a wheel designed and mounted to utilize these properties is called a gyroscope. These of the gyro wheels are called gimbals. It is these gimbals or mountings that allow the spinning mass to exhibit the two fundamental gyroscopic properties, rigidity in space and precession. Rigidity in space is the resistance of the spinning mass to being moved or displaced from its plane of motion. Once set in motion, the gyro tends to maintain its orientation in space regardless of the movement of its base or point of attachment to a moving object. Mounting the gyroscope in gimbals that can be attached to a base such as an airplane allows the gyroscope to remain rigid in space as the airplane moves around it. The gyroscope remains in the same position relative to the Earth. Indications on the instrument's face, which are attached by various mechanisms to the gyro itself, tell you the position of the airplane relative to the gyro and hence relative to the Earth. The instruments using the gyroscopic property of rigidity are the attitude indicator and the heading indicator. Precession is the movement of the gyroscope's spin axis from its original position due to some external force. A spinning mass reacts 90 degrees away from the point of contact with the external force. This results in a wobble or altered plane of rotation. Without becoming physicists, we must at least recognize that some airplane movement will cause precession and result in occasional display errors. But it's not all bad. One instrument, the turn coordinator, uses precession to provide the desired information. Later in this lesson, we will deal with the recognition of precession error and learn to adjust the instrument as necessary to regain an accurate reading. There are two commonly used power sources for gyroscopic instruments. The engine-driven vacuum or air pressure system is used because it is a simple, reliable system and is usually the power source for two of the three gyro instruments. The third gyro is usually powered by a small electric motor inside the instrument. The vacuum or pressure system spins the gyro by drawing a stream of air against the rotor vanes to spin the rotor at high speeds. This is essentially the way a water wheel or turbine operates. The electrically driven gyro is run by a small electric motor attached to the gyro and powered by the airplane's electrical system. This is usually the turn coordinator. Two different power sources create redundancy. That is, if one type of power source fails, you still have some gyro instrument available. Redundant systems are very common in airplanes, and you will learn more about others during this course. Now, let's take a look at the gyroscopics individually. The attitude indicator is also referred to as the artificial horizon or gyro horizon. Most attitude indicators on light airplanes, like the Skipper, are air-driven. The attitude indicator provides the pilot with a visual picture of the airplane's pitch and bank attitude with respect to the horizon. It consists of an airplane silhouette fixed to the face of the instrument and therefore aligned with the airplane itself, and a graphic representation of the horizon which is attached to the gyro. So when using the attitude indicator, the horizon remains stable as the airplane moves around it. The airplane on the attitude indicator moves with the real airplane to which it is attached. An adjustment knob allows it to move the miniature airplane up or down to align it with the horizon bar to suit the pilot's line of vision. The area above the horizon bar represents sky and is frequently blue, and the area below the horizon represents the ground. Unlike the pitot-static system instruments, there is no delay or lag in the display of information. The attitude indicator provides instant indications of even small changes in pitch and bank. For exact bank information, there is a bank index on the face of the instrument with markings for the degree of bank. 0 degrees, 10 degrees, 20 degrees, 30 degrees, and 60 degrees. Angle of pitch can be read on the instrument face above and below the horizon line, from 15 degrees nose up to 20 degrees on. For example, when your airplane is in straight and level flight, the attitude indicator will show wings level and the nose on the horizon. In a left climbing turn, the attitude indicator shows the degree of bank and the nose above the horizon. This attitude indicator shows a left climbing turn of 30 degrees bank with a 5-degree nose-up attitude. In this example, the plane starts a climbing turn of 20 degrees bank to the right with a 15-degree nose-up attitude. The pilot increases the turn to 30 degrees angle of bank before returning to straight and level flight. Earlier in this lesson, we talked about the principle of precession. Precession does affect the attitude indicator, but due to an internal mechanism found in most modern attitude indicators, the instrument can correct this tendency and remain rigid and upright at all times. But everything has its limits. This instrument will simply wear out and eventually give erroneous indications if it is continually subjected to excessive angles of pitch and bank. The turn coordinator picks up where the attitude indicator leaves off. It provides rudder or yaw information, turn direction, and rate of turn information. It does not present pitch information. The turn coordinator uses the principle of precession to provide the desired information. This is really two instruments in one. The upper gyroscopic indicator displays the rate of turn and the direction of turn. The bottom portion, sometimes referred to as the ball, but more correctly as the inclinometer, displays the yaw information. The turn coordinator shows a miniature airplane, reference marks, and the words 2-minute or 2-minute turn. When the airplane is banked so that the wingtip is lined up with one of the lower reference marks, your airplane will fly a full circle in 2 minutes. This is a standard rate turn and is equivalent to turning at 3 degrees per second. When the miniature airplane's wings are lined up with the two wings level marks, the turn rate is 0. The inclinometer, or ball, is a self-contained instrument and is the only instrument that gives you rudder information. Like a carpenter's level, it responds to the force of gravity as well as centrifugal force. If too much rudder is used to counter adverse aileron yaw when rolling into or turn, the ball goes toward the outside of the turn. The airplane is actually skidding. If too little rudder is used, the ball goes to the inside of the turn and the airplane is slipping. To correct either condition, simply step on the ball until it centers. This means to use the rudder pedal on the side on which the ball is located. But the ideal turn is one where the rudder is used so that the ball never strays from between the index lines. The turn coordinator is extremely reliable because of the gimbal structure, and this is the gyro instrument that is usually electrically powered. The heading indicator is the last of the 3 gyroscopic instruments. This is not the airplane's magnetic compass, which we will explain shortly, but rather an instrument designed as an easy-to-read indication of direction, free from magnetic compass errors. Most heading indicators show an airplane symbol on the face, which is over a 360-degree azimuth card connected by gears to the gyro itself. The azimuth card shows the cardinal headings, north, east, south, and west, with 30-degree increments labeled numerically. Notice that the last digit, a 0, is omitted. The 3 represents 30 degrees, 6 is 60, 12 is 120, and so on. Each of the 30-degree increments is divided into smaller 10 and 5-degree calibrations. The heading indicator is used in conjunction with the magnetic compass and is periodically checked with and set to the compass reading. We use a gyroscopic heading indicator during flight to maintain headings, to facilitate reading heading information during turns, or while in rough air. The heading indicator, like the attitude indicator, is usually an air-powered gyro that uses the principle of rigidity in space to maintain stability. As the instrument case and the airplane revolve around the vertical axis, the card provides clear and accurate heading information. Except for situations involving excessive angles of bank or improper setting, this instrument is extremely reliable. Precession does act on this instrument, but unlike the attitude indicator, the heading indicator does not have the internal capability to correct for precession errors. Consequently, the azimuth card will drift from its correct setting during flight. This gyro drift requires the pilot to reset the heading indicator to a reliable source of heading information, such as the magnetic compass. This is done using the small knob on the left. This knob is attached to the azimuth and turns the card in either direction. It is important to check the indications frequently and reset the heading indicator to align it with the magnetic compass when necessary. Flying from Petaluma to Tracy on a magnetic heading of 110 degrees, we find after a while that our heading indicator shows steady on 110, but our compass indicates 117 degrees. So we turn the azimuth card on the heading indicator to 117 degrees, then turn the airplane until our heading indicator reads 110 degrees. The rule of thumb is that the heading indicator should be set every 15 minutes, and the drift should be no more than 3 to 5 degrees each 15 minutes. This should be done only when the airplane is in full, unaccelerated flight. Otherwise, erroneous magnetic compass readings will be obtained. All of the instruments we've discussed, except the inclinometer, have required some external source of power. The magnetic compass and the outside air temperature gauge are self-contained instruments and do not require any external power source. The magnetic compass is usually mounted above the instrument panel and is the only instrument that provides the pilot with actual directional information relative to the Earth. Inside the compass are 2 steel magnetized needles fastened to a float around which is mounted a compass card. Most magnetic compasses display the cardinal headings, north, east, south, and west, 30-degree increments labeled numeric, and smaller 10 and 5-degree increments as on the heading indicator. You'll notice that the compass appears to be backwards. West is right of north. East is left of north. That's because the airplane moves around the magnet to which the display is attached. You will see a line called a lubber line mounted behind the glass, which can be used for a reference when aligning the headings on the compass card. There are certain limitations to the use of the magnetic compass, most of which can be compensated for either in flight or during flight planning. These include variation, deviation, magnetic dip, turning error, acceleration error, and oscillation error. Variation is the difference in degrees between magnetic north and true north. The amount of variation is different for different points on the Earth's surface and is important because aeronautical charts are aligned with true north. Variation is shown on the aeronautical charts as broken lines connecting points of equal variation. These are isogonic lines. They are labeled with the amount of variation in degrees and the cardinal symbol E for east or W for west, indicating where the variation is with respect to true north. The line of zero variation is called the agonic line. All locations west of the agonic line have easterly variation. Locations east of the agonic line have westerly variation. This is taken into consideration during flight planning, and the amount of variation is either added to or subtracted from the true course of a flight to a desired magnetic course. Easterly variation is subtracted from true course, and westerly variation is added. In this example, the isogonic line shows a 16-degree easterly variation. A free-floating magnetic compass, unaffected by outside forces, will always point to magnetic north. In an airplane, however, small but measurable magnetic fields may be created either by metallic or electrical components in the cockpit. This results in deviation. A compass correction card is attached to the compass case to list the exact amount of deviation for a given heading. Since all airplanes, even those of the same type, may have slightly different metallic or electrical components, the compass correction card is applicable to that compass in that airplane. Unlike the heading indicator, which is governed by the rigidity and space qualities of a gyro, the magnetic compass is always oriented to the Earth's magnetic field. The lines of the Earth's magnetic force run generally parallel to the Earth's surface between the north and south magnetic poles. The north-seeking end of a free-floating magnet, such as in an airplane, will always point directly to the magnetic North Pole, parallel to the lines of magnetic force. Note that in the northern hemisphere, the north-seeking end of the magnet will tend to dip or seek the ground. The amount of dip increases as the magnet is moved closer and closer to the poles and the force gets correspondingly stronger. Magnetic dip accounts for two important compass limitations: error and acceleration error. Turning error occurs when turning from northerly or southerly headings. When turning from a heading of north, the bank allows the north-seeking end of the magnet to dip, which causes the compass display to show a slight turn in the wrong direction. As the turn continues toward east or west, the effect of this error decreases. The opposite happens when turning from a southerly heading. Dip causes the compass to show a turn in the correct direction, but at a seemingly faster rate. As you approach east or west headings, the result of this error also decreases. The second dip error is called acceleration error. When on an east or west heading, acceleration will cause magnetic dip to create an indication of a turn to the north. Conversely, deceleration will cause an indication of a turn to the south. The acronym AND will help you remember this. Accelerate north, decelerate south. Since the compass must be free-floating to work at all, it is subject to what we call oscillation error. It is very prone to swing back and forth or oscillate and can be very difficult to read during turbulence or rapid flight maneuvers. The actual magnetic heading is usually midway between the extremes of the oscillation. By addition, the magnetic heading on this compass could be estimated as 180 degrees. In order to help dampen some of this oscillation, the float assembly of the compass is housed in a bowl of acid-free white kerosene. So always make sure your compass has fluid for proper operation. The magnetic compass is very reliable. It is best used as a directional reference for the heading indicator. Because of both dip and oscillation error, however, you should only use the magnetic compass for heading information when the airplane is in unaccelerated, straight and level flight. The outside air temperature gauge, called OAT, is the last of the flight instruments we'll discuss. It is usually located in the windshield. It works like your home thermometer and has scales for both Fahrenheit and Celsius measurement. The outside air temperature gauge is used for replanning cross-country information in flight and determining airplane performance. It is obviously a great help for indicating temperatures when ice may be a hazard. While we have discussed the flight instruments individually, it is clear that the pilot will benefit most from their combined information. In-flight work with your flight instructor will better help you understand and make good use of the total information they provide. In addition to the flight instruments, you as pilot will see many more dials and gauges on the instrument panel. Some of these refer to engine operation, some are navigation equipment, and there are electrical switches and circuit breakers. Most of the engine instruments are located in the center of the airplane's instrument panel. Included are the left and right fuel quantity gauges, temperature gauge, oil pressure gauge, fuel pressure gauge, and ammeter. You will usually have all of these instruments and gauges in any basic trainer you fly, although they may be placed in different locations. In your flight training, you will learn to monitor these instruments regularly during flight. You cannot allow any temperatures or fluid levels to deviate from a normal operating range, so constant observation is needed. Directly above these engine instruments is the tachometer. This displays the engine's RPM, revolutions per minute. The gauge shows a safe operating area, usually green, and a danger zone above the red line. Do not operate any engine in the area above the red line. Engine controls are located just below the engine instruments. The knobs are shaped to government standard configuration, so they can be identified by touch. Color coding is also used. The mixture control is red and has a scalloped shape. The carburetor heat control is a much smaller knob, which is a sort of oval or football shape and is black. The throttle control is a round shape and has a black knob. In addition, numerous switches and circuit breakers appear, usually on the lower portion of the instrument panel. Generally, they include a key magneto, start, and position switch, a battery and alternator switch, and light switches for landing, exterior strobe, and navigation lights. The number and function of switches will vary from manufacturer to manufacturer and from plane to plane, but you will quickly become familiar with them during your flight training. Circuit breakers and/or fuses are included for most of the plane's electrical functions. The center or slightly right of center is usually where the avionics equipment is placed. Basic communication requires a two-way radio and is usually combined with navigation capability and a VOR receiver. In today's flight environment, a transponder is very helpful, and you will find this located with the avionics equipment. We will discuss operation and use of this equipment in a later program. Circuit breakers for the avionics are also located in this area. Now we've examined the three categories of flight instruments and included a brief look at the total instrument panel. Don't let the number of instruments, dials, and gauges scare you. They're really a lot of fun to use and provide a measure of safety for modern-day flying. When the Wright brothers finally got their airplane off the ground at Kitty Hawk, they had three factors in their favor: a crewed catapult, a 12-horsepower engine, and a prayer. If you've seen pictures of the aircraft they flew, you would probably agree that the prayer was the most effective part of the combination. During their early stages of development, power plants and their related equipment were very simple in construction and often inadequate. Their reliability factor was very low, and engine failures were quite common. Today's power plants are not simple in construction or operation, but their reliability factor is very high. As a private pilot, you must have a good working knowledge of general aviation power plants. Ken Blust is highly respected as an educator, in addition to working professionally as a licensed A&P mechanic for many years. He is an instructor at the College of San Mateo. Ken also is a private pilot, and of course maintains his personal aircraft. Hello, Ken.
Hello, Jeannie.
How are you?
Fine, thank you.
Good. I'm really glad that you could be with us today to help us understand what some people think is a very complex piece of machinery, the aviation power plant.
Well, it's not really all that complicated, Jeannie. We have the basic four-cycle air-cooled engine, And then we have the supporting systems. We have the ignition system, the fuel system, the lubrication system, the electricals, the cooling system, and of course the propeller, which provides the thrust to drive us through the air.
Ken, for those who are not familiar with the four-stroke reciprocating engine, can you tell us briefly how it operates?
Yes, it's very similar to your automobile engine. The four-stroke engine, the pistons are connected to the crankshaft through the connecting rods, and as the pistons move down in the cylinders, this provides the rotating motion that drives the propeller. We have our four basic strokes: the intake stroke, the compression stroke, the power stroke, and then the exhaust stroke. And of course, these repeat very rapidly in sequence. Let's take a little closer look at each one of these individual strokes. On the intake stroke, the intake valve is open and the piston is moving down in the cylinder. And the fuel-air mixture then is forced in by the higher pressure on the outside and the low pressure in the cylinder. As we come to the bottom of the stroke, the piston then starts moving up on the compression stroke, and the valves are both closed at this time. The fuel air then is compressed, and as we approach the top of the stroke, the spark plug ignites the fuel-air mixture, and then we start down on the power stroke. And as the fuel-air mixture is ignited, it expands, and this force is transmitted down to the piston as it moves down on the power stroke. As we reach the bottom of the power stroke, then the exhaust valve opens, and the piston starts moving up again into the exhaust stroke, and this forces the burnt fuel-air mixture out of the cylinder. And as we reach the top of the exhaust stroke, we've completely exhausted the burnt fuel-air mixture, and then we're ready to start over again on the intake stroke. Let's see a little bit more about the detail of how the power is actually transmitted through this system. As the piston moves down on its power stroke, it's connected by a connecting rod to the crankshaft. The reciprocating motion of the piston is converted to rotary motion by the crankshaft. And the crankshaft is in turn a propeller. And as the crankshaft rotates, then the propeller develops its thrust. And we have in this engine 4 cylinders, so they fire alternately, so we have a fairly steady supply of power to the crankshaft to rotate the propeller and give us our thrust.
Of course, an engine runs on fuel, but how does the fuel get from the tank to the engine?
Normally the fuel is stored in the tanks in the wings, then it's transported through the various plumbing, through the strainers, the pumps, and the carburetor, and then to the engine. We generally have two types of systems. We have a high wing system and a low wing system. In the high wing system, usually it's a gravity feed. The gravity will cause the fuel to flow from the tanks down to the engine. Occasionally you may have a pump. In the low wing system, you have normally two fuel pumps. One is an electric pump and one is an engine-driven pump. The electric pump is a backup for the system. It also is used in starting the engine when you don't have the fuel from the engine pump. As the fuel is collected in the tank, there's a low point in the tank. This is the fuel tank drain. If any water condenses in the tank, it can be drained out at this point. From there, the fuel travels through the selector valve, and the pilot in the cockpit then can select the tank for the appropriate operation. From there, it goes to the fuel strainer. This is the low point in the system, and the aircraft will have a drain on this point, and during the pre-flight you can drain the fuel from there, and if there's any water that condenses in the system, it can be drained out at this low point, since it will settle there as water is heavier than fuel. And from there it goes up to the engine-driven pump and on to the carburetor. The system quantity will be indicated by a fuel quantity indicator system in the cockpit to tell you how much fuel is in each tank. If you find that the fuel quantity indicator is inoperative, you must get it repaired, because this system is required to be operative according to the Federal Aviation Regulations. In some cases we may have a fuel pressure indicating system and also a fuel warning light that tells us if the fuel pressure is low.
Ken, we know there are different grades of fuel for automobiles. Can you tell us a little bit about the different grades of aviation fuel?
That's right, Jeannie. The aviation grade fuel comes in 3 different grades: 80 octane, 100 octane, and 100 octane low lead. Now, the octane ratings are an indication of its anti-detonation characteristics, or how it will perform in the combustion chambers of the cylinders. So the 80 octane has a lower anti-detonation characteristic than 100 octane.
And how can we tell the difference in those fuels?
Well, if you notice by our samples here, the 80 octane is red, 100 octane is green, and the 100 octane low lead is blue. These colors are put in by the manufacturer when they manufacture the fuel. And this is a distinctive color for this fuel. It's a way of identifying it. When you drain the fuel on your pre-flight, you should use a transparent container. So as you drain the fuel into it, you'll be able to check and find out what type of fuel is in the aircraft. Your operator's manual will specify the particular grade of fuel that is to be used in your airplane, and you should always follow this.
What happens if you can't get the right grade of fuel that you need?
All right. In quite a few areas now, 80 octane is no longer available. The manufacturers have quit manufacturing it. So in most cases then we will go to 100 low lead. But remember, consult your pilot's operating handbook. If we mix 80 octane and 100 octane and we're using it in an aircraft such as the Skipper, which requires 100 octane, then we're lowering that characteristic. So there's possible that we could create a situation where we can get detonation in the engine, and this will cause structural damage to the internal parts of the engine.
How can we tell? How do we know if the fuels have been mixed?
Well, when the dye is put into the fuel, this dye is such that if we mix the fuels, and I'll show you how that works, if we mix the fuels in, then the color will change. The color tends to disappear, and the liquid fuel then should become from, oh, say a clear to a straw colored. And so when you take your fuel sample, if it's clear or just slightly yellowish, then you know it's been contaminated. And again, by referring to the manual on the airplane, you will know if this is acceptable or not. On the Skipper, for instance, it requires 100 octane, so if we find a fuel sample that's clear, then we know it's been contaminated with a lower grade fuel, and we shouldn't fly the airplane till this has been corrected.
It takes a little while for that color to change, doesn't it?
Yes, it does, and usually in larger quantities it will mix, such as the tanks of the airplane where it's been mixed. Why, you'll notice it'll be noticeable. If we do mix the wrong grades of fuel in there, then detonation can occur. Now, detonation is a characteristic, as I said, of the fuel as it performs in the combustion chamber. Normally what happens in the combustion chamber is that the fuel-air mixture is ignited and it burns slowly across the fuel-air mixture. And this provides an even pressure on the piston to push the piston down and give us a good uniform pressure in there. Detonation occurs when normal burning starts, and then the fuel-air mixture explodes, and this gives us a very sudden shock to the engine. In fact, in automotive engines, when you hear it ping, that's detonation. And so detonation can be caused by that. Detonation can also occur if we use automotive gas in the airplane. We should never mix automotive gas in your airplane. Besides being against the regulations, the FAA says this is not the way to do it, and it will cause a problem with detonation possibly. So do not ever mix aviation gasoline with automotive gasoline when you're going to use it in your airplane.
Can you show us some of the problems caused by using the wrong grade of fuel?
Let's take a look at this piston. This has been badly scored from overheating. Detonation can cause the piston to overheat, and it can cause the expansion rates to be such that it's going to interfere with the cylinder walls. The heat will tend to cause the lubrication to leave, and we get severe scoring. This would cause a loss of power in the engine. Another thing that may occur is damage to your valves. Actual burning of the valves due to the excessive heat and pressure that builds up in the cylinders when detonation occurs. There's also another thing that can occur along with this, and that is pre-ignition. Pre-ignition occurs when the fuel-air mixture is ignited by a hot carbon deposit or other source prior to the timed ignition. This causes a rapid rise in cylinder pressure and temperature. If we have a severe case of this, we may even have a cylinder failure, such as this one, where the pressure was built up so much that it actually fractured the cylinder head. The cylinder head would then fail, and we'd have probably a total engine failure. This was likely to occur, say, on takeoff, when it's very critical for the pilot to have his engine.
And it gets suddenly very quiet.
Right.
Ken, we've talked about fuel in the tanks. Now, what is the next step?
The next important step we come to is the carburetor. On this cutaway, I can show you a little bit about the operation of the carburetor. In most of your smaller aircraft with simple engines on, they use what they call a float carburetor. This is what the Skipper has on it. The fuel comes into the float chamber, and then the fuel travels down through the mixture control, through the metering valve, and up through the discharge nozzle, and it's mixed with the air in the venturi. As the air travels through the carburetor in response to the opening of the valve, we create a low pressure in the venturi, similar to what we create over the top of the wing. So we have atmospheric pressure in the float chamber, we have low pressure in the venturi. The fuel is forced then up through the metering jets and out the discharge nozzle in the venturi. Here the fuel is atomized and mixed with the air and then taken onto the intake pipes and into the cylinders.
And of course, this is the area where we're concerned about icing.
Right, Jeannie. If icing occurs in a carburetor, it occurs from the phenomena of causing the liquid to go to a vapor. So normally what happens is, as the fuel is coming out and being vaporized, it absorbs the heat out of the surrounding air. This lowers the temperature of the air and its ability to hold moisture. So the moisture tends to condense out on the throttle plate and in the venturi. And the temperature can drop enough now that this moisture that's condensed out will start to freeze. If this happens, what we're going to notice in the engine is that we're going to notice a drop in RPM and possibly some roughness because it's disturbing the airflow, cutting down on the amount of fuel that's going to the engine. So to correct this, we have a carburetor heat control in the cockpit. As soon as you notice that you're getting this indication of carburetor ice, you should put the carburetor heat on full. And then what's going to happen is the warm air is going to come through here. We're going to get a slight decrease in RPM from this because of the warm air going in, and as the ice melts out, then we're going to get our RPM picking back up and the engine should smooth out if it's been rough. Now we can get carburetor icing and temperatures maybe up as high as 90 degrees and with no visible moisture. We don't have to be flying through a cloud. Ordinarily there's enough moisture in the air that this phenomenon can occur.
And what happens if we don't take care of carburetor ice?
Well, we can block off the airflow, and remember it was a low pressure in the venturi that caused the fuel to flow, so if we decrease the low pressure in here, we're going to decrease the fuel flow, and this is going to end up in engine stoppage.
And it gets very quiet.
Very quiet.
I understand fuel injection systems avoid the problem of carburetor icing.
That's right. The majority of the problem of carburetor icing is eliminated with fuel injections. Jeannie, I'd like to show you this engine. It's a 4-cylinder air-cooled engine similar to the Skipper, but it has a fuel injection system on it, and I think we can show you how it cuts down on the problem of carburetor icing. The fuel injection system has a fuel control located here. This is the point where the fuel is measured and the air is measured, but the fuel is not mixed at this point. The fuel is brought out by an external line up to the flow divider, and here it's divided up equally to each cylinder, and then it travels out to the cylinder through this line and is injected through into the intake port. Now the air comes in through here. When the intake valve opens, the fuel-air mixture is forced into the cylinder. And since we don't mix the fuel and air in the carburetor, here we have the fuel control unit that simply measures them. We eliminate that problem of the carburetor where the temperature drop occurs and icing would occur. The problem that is possible to run into with any carburetor or fuel injection system is impact icing, when we have structural icing on the aircraft flying through freezing rain and that type of thing. Let's go over to the Skipper, Jeannie, and I'll show you how the ignition system works.
All right.
In an aircraft engine, we have dual ignition. There are two reasons for the dual ignition system. One is safety and one is for more efficient operation. We have two spark plugs located in each cylinder. These spark plugs, when they both fire, give a more even and complete burning of the fuel-air mixture. This gives us our better efficiency. The safety aspect of it is that if one system fails, we can run the engine on one system alone. There is one magneto located on the accessory case that fires one of the spark plugs in each cylinder, and the other magneto located on the other side fires the other spark plugs in the cylinder. So they're two separate independent systems. These are controlled by a switch in the cockpit. During your operation just prior to takeoff, you're going to check the mags for operation. So by switching the switch in the cockpit, you can operate on one magneto, and this will show you by the drop in the engine RPM whether that magneto is operating correctly or not. And then you can check the other one.
Why don't we take the Skipper out and give it a mag check?
Okay. right, now we're going to do a magneto check. Actually, there's two things we're going to check. We're going to check the continuity of the switch wiring, and then we're going to check the actual operation of the magnetos and spark plugs. So we'll go ahead and start the engine up. Now the engine RPM is stabilized at about 1,000 when our oil pressure is up. So the first thing we're going to do is check the continuity of the switch wiring. Now, we will move the magneto switch to left and the engine should continue to run. We move it to right and it should continue to run. And we turn it momentarily to off and the engine should stop. And we switch it back on before the engine completely stops. All right, so that checks our magneto wiring. We know it's good. Run the engine up to the magneto check RPM, which is 1,800 RPM on this airplane. We take it up to 1,800 RPM and let it stabilize, check sure our pressures and temperatures are stabilized. And then we switch it to the left mag and note the mag drop. We have about 125. The maximum for this is 175. And we switch the switch to both, and then we switch it to right, and again we'll note the drop. And we have about 125 drop there. And then we switch it back to both and let the engine stabilize. Now there are two things in this that we have to watch for. We have the maximum drop on either mag of 175, and they also have to be within 50 RPM of each other in their drop. If either of these conditions go out of the limits, then we will have to have the mechanic check this and correct this discrepancy before flight. Okay, now we can bring the engine back to about 1,200 idle position and let it stabilize. And go ahead and shut the engine off. All right, Jeannie, now all the switches are turned off, and let's go outside and we'll take a look at the electrical system.
Okay. Ken, what are the major components of the electrical system?
We have the battery and the alternator and the voltage regulator, and the fuse blocks and the associated switches and wiring. The battery is located right here in this sealed battery box, and this is where the electrical charge is stored when the aircraft is not operating. The alternator is located on the front of the engine and is driven by this belt. Be sure you check this belt on pre-flight, because if the belt is damaged or missing, then you won't have any alternator operation. The fuse blocks here protect the various circuits from overload. If we get an overload in one circuit, why, the fuse will blow and it will protect the aircraft circuit from possible fire. Inside we have the voltage regulator.
Okay.
The voltage regulator is located right here. It controls the output of the alternator and keeps it at about 14 volts, and this keeps the battery at its proper charge when the engine is operating. In the normal operation of the electrical system, the battery supplies the power when the engine is not running. This allows us to operate the starter and the fuel pump to get the engine going. When the alternator output will be charging the battery and supplying the electrical system with its needed voltage. In case of a heavy demand on the system, then the battery can also assist the alternator, but the normal output of the system is supplied by the alternator during the operation of the system.
Ken, with the tremendous heat energy that an aircraft engine develops, the cooling system is very important. Can you describe the skipper's cooling system to us?
Yes, Jeannie. The skipper has an air-cooled engine, and the air enters through this port and the port on the other side. It enters into this chamber, and with the top and this baffling, it forms a high-pressure area here. The baffles keep the air from flowing out the back of this chamber. And the high-pressure air then is forced down through the cylinder fins. This carries away the heat, and it exits out the bottom. A great deal of the heat can also be carried away by the oil system.
Ken, you mentioned how the oil helps to cool the engine. Can you tell us a little more about that and the importance of the lubricating system?
Yes, Jeannie, the major function of the oil is, of course, lubrication. The oil is circulated through the engine under pressure, and this helps to prevent metal-to-metal contact of the moving parts. The oil carries away a lot of heat during this process, too. The oil cooling air comes in here, travels through this duct down to the oil cooler, where it picks up the heat from the oil and then goes overboard. The oil is serviced and checked through the oil filler. Be sure that you use the proper grade of oil, and be sure to check your oil level before each flight. If you'd like to step over here, I'll show you a little more about engine oil. Generally speaking, we have two types of oils. We have a straight mineral oil, and this would be comparable to what we would use in a car and call it a non-detergent oil. And then we have the non-ash dispersant oil, and this would be similar to a detergent oil in the car. Not only does it perform the function of lubrication, it performs a function of cleaning at the same time.
What would happen then if you mix these oils?
Well, if your engine has been operating on a straight mineral oil, it accumulates a considerable amount of carbon deposits inside the engine, and they're fairly tightly adhered to the surface. But if we put then the non-ash dispersant oil in, it does its job of cleaning, and it loosens these particles, and there's a possibility that we might have some of the oil passages in the engine clogged up, and we might damage the internal parts of the engine due to lack of lubrication.
Not too good if it happens in flight.
No, not really. Besides this, we also have the different weights of the oil or viscosity of the oil. It is marked on the top of the can, and we should be just the proper viscosity specified by the manufacturer. The viscosity is a measure of the oil's resistance to flow. The higher the viscosity number, the more resistance it has to flow. Some of the manufacturers are now coming out with multi-grade oils, and this type of oil acts as a low viscosity oil at a low temperature and as a high viscosity oil at a high temperature. This also enables you to operate your airplane from a low temperature area to a high temperature area without changing the grade of oil you're using. I can show you how this viscosity works if you want. As we pour the oil down here, you'll see that the oil with a high viscosity flows rather slowly, and the oil with a low viscosity flows fast down here. So the viscosity is the measure of the internal resistance of the oil to flow.
Ken, everything we've talked about up to this point has been leading up to developing thrust for the propeller. Can you tell us a little bit about propellers?
Yes, Jeannie. Normally we have two types of propellers. One is the fixed pitch propeller like the Skipper has, and one is a constant speed propeller. The fixed pitch propeller that the Skipper uses will develop its maximum thrust and torque at a particular RPM and speed. With a constant speed propeller, the pilot can actually adjust the blade angle so that during climb, cruise, takeoff, he can adjust his angle of blade so that he can get the maximum performance out of his propeller at all time. This gives us much more efficiency as far as the propeller is concerned.
Ken, I think we've just about covered everything.
I believe so, Jeannie.
Well, I really want to thank you for being with us and sharing your knowledge. It's been a great pleasure.
Well, it's been my pleasure too. Thank you, Jeannie.
We've covered the basics of power plant operation, and though you are not expected to be a certified A&P mechanic, your understanding of these basic systems is extremely important. You will find some information and specifications about your airplane in the pilot's operating handbook, but when in doubt, consult a certified A&P mechanic. Remember, a properly maintained aircraft is a safe aircraft, and a solid background in the systems we've outlined will be essential to you as a pilot to assure your safety and the safety of others.
I sure appreciate you flying me up to Sacramento. It's going to save me a lot of time.
Well, I'm delighted. I was going up anyway, and it'll be nice to have the company.
This meeting came up at the last minute, and I couldn't make any other arrangements.
Well, that's the time when it's good to go by air. There, if you want to just put your things back in there, and then I'll do a pre-flight.
You got lots of room back there.
It's pretty roomy for a little guy.
I thought as long as we had the extra room, I'd take a few more samples.
Well, it's not the room that's the problem, it's the balance.
Well, they don't much.
No, but it will affect the airplane's balance.
I don't understand how just a few more pounds will make any difference.
The concepts of weight and balance and how they relate to the airplane are relatively simple, but critical to safe flight. The easiest way to explain this relationship is to use a child's teeter-totter. When two children of about the same weight climb on the teeter-totter about the same distance from the pivot point, they balance each other, and the kids use this balance to ride comfortably for hours. The same concept is true for any weights placed on a board attached to a pivot point. Equal weights placed the same distance from the pivot point will balance. If there is no weight on one end, the end with the weight stays on the ground. If one weight is heavier than the other, the end with the heavier weight stays on the ground. Only when the weights are equal will the board balance. The distance of the weight from the pivotal point is called the arm. The pivotal point itself is called the fulcrum. The force of the weight acting on the board is called moment. Of course, a heavier weight means a greater moment. But just as important, a longer arm means a greater moment. This is why a 100-pound child has to sit half as far from the fulcrum as a 50-pound child if they are to balance. The force produced about the fulcrum is the same. You don't have to be a whiz at math to understand that weight times arm equals the value we call moment. Using this formula, let's work problems. If the weight on the teeter-totter is 100 pounds and its location is 10 feet from the fulcrum, what is the force of the weight acting on the board? Or, what is the moment? Using the formula, weight times arm equals moment, we simply fill in the known values. Weight being 100 pounds, arm being 10 feet, multiply weight times arm, and the moment value is 1,000 foot-pounds. Here's another problem. Let's place 200 pounds located 50 feet from the fulcrum. Then, 200 times 50 equals 10,000. Now let's relate this idea to the actual airplane. The position of the fulcrum of the teeter-totter is comparable to the airplane's center of gravity. The center of gravity is not a static position. It will move forward and back on the location and weight of various items placed in the airplane. For example, the fuel, the pilot, cargo, and the passengers. Just as a teeter-totter will not balance unless the weights are placed in a proper position, the airplane will not fly properly unless it too is within a certain range of limits. If the momentum either side of the airplane's center of gravity is too great, the center of gravity actually moves, and if it moves too far, undesirable and dangerous flight characteristics might exhibit themselves. The airplane designers took all this into account when they designed the airplane. The pilot's responsible for ensuring that the airplane's properly loaded and remains within the center of gravity limits established for the airplane. To assist the pilot in his determination of the center of gravity location or balance point, the designer provides a reference point from which to measure the location of the various weights loaded on the airplane. The
point is called the datum or datum line. Most datum lines are located on or near the nose of the airplane, and for purposes of weight and balance computations, the plane is always oriented to the left. This makes these computations standard and easier to visualize. Objects placed aboard the airplane and the airplane's center of gravity are measured in inches from the datum.
The location of the datum is arbitrary, and it may even be located with the weight objects placed in front of it, like it is for this twin-engine airplane with a nose baggage compartment. In that case, the arm will have a negative value as well as the moment. Once we have the arm of all the objects aboard the airplane, we can use our previous formula of weight times arm to arrive at a moment value for every object aboard the airplane. Basic empty or licensed empty weight of the airplane and its moment is obtained in the current weight and balance information. Then it's simply a matter of adding the various weights together and the moments together and dividing the total weight into the total moment. The answer is the airplane's total weight and the arm, or the distance from the datum of the airplane's center of gravity.
Before we look at the big picture of the airplane's weight and center of gravity limits, we need to define some terms.
Basic empty weight is the weight of the airplane complete with all installed equipment, engine oil, and unusable fuel. Unusable fuel is the fuel remaining in the tanks after a run-out test has been completed in accordance with governmental regulations. This unusable fuel is considered part of the airplane's own weight. The weight of fuel is 6 pounds per gallon, and the weight of oil is 7.5 pounds per gallon. These are two important values for the pilot to remember. The airplane's basic empty weight is found in the weight and balance data required to be aboard the airplane. If the term licensed empty weight is used instead of basic empty weight, you should know that the oil is not part of the empty weight. You must add this in your computations. Useful load includes everything that can be added to the airplane until its maximum weight is reached. This includes usable fuel plus payload. Usable fuel is the weight of the fuel aboard the plane that is available to the engine. Payload includes the weight of the passengers, cargo, and baggage. Maximum ramp weight is the maximum weight approved by the manufacturer for ground maneuvering. Maximum takeoff weight is the maximum weight approved for the start of the takeoff run. Maximum landing weight is the maximum weight approved for the landing touchdown.
Before we can actually take off on a safe and legal flight, two important questions must be answered. Is the airplane's weight within the manufacturer's maximum allowable gross weight? And is the actual center of gravity within the manufacturer's allowable center of gravity range? We will answer these two questions using three basic methods of solution: the computation method, the tabular method, and the graph method. The computation method appears to be the most complex of the three because of the amount of arithmetic involved. But these computations are the basis of the pilot's operating handbook tables and graphs. Let's assume a four-place airplane that has a maximum gross weight for takeoff of 2,450 pounds. First step is to make a list of everything you intend to load aboard the airplane and note its actual weight.
The airplane's basic empty weight is 1,500 pounds. Its fuel, 35 gallons at 6 pounds per gallon, is 210 pounds. Two front passengers weigh 340 pounds. Two rear seat passengers weigh 340 pounds. The baggage, 60 pounds. Always use actual weights of people and baggage.
Although the airlines can safely use a standard weight of 170 pounds per passenger, even one person's weight difference from standard affects the general aviation airplane's performance. With the list completed, add all the item weights together. This gives you the total gross weight. The total takeoff weight is 2,450 pounds. As you can see, the total load does not exceed the manufacturer's maximum limit of 2,450 pounds. So far, we've only answered one of the two questions. Is the center of gravity location also within the allowable limits?
In order to find the center of gravity location, we must consult the pilot's operating handbook for our particular airplane to find the arm for each item on our weight list. The datum was established by the manufacturer at the nose of the airplane. The Sundowner's datum is located left of the nose, making the fuel arm 117 inches. Establish your chart to reflect all weights and distances. Basic empty weight, 1,500 pounds times 110 inches. Fuel, 210 pounds times 117 inches. Front passengers, 340 pounds times 112 inches. Rear seat passengers, 340 pounds times 142 inches. Baggage, 60 pounds times 167 inches.
Now, simply follow the formula. Weight times arm equals moment. You should have a worksheet that looks like this. Now, simply total the figures in the moment column just as you did the weight column figures earlier. The result is 285,950. Now we have all the information we need to locate the center of gravity of the airplane. Since weight times arm equals moment, it follows that moment divided by weight will equal arm. So divide the total moment by the total weight. The result will be the total arm, or the location of the center of gravity of the total loaded airplane. The answer is 116.7 inches from the datum. We must now once again consult the pilot's operating handbook to find out if, for the weight already calculated, the center of gravity falls within an acceptable range.
For 2,450 pounds gross weight, the center of gravity numbers should be between 114.5 inches and 118.3 inches from datum. We successfully complied with both areas of concern, total weight and total balance, using the computation method. Now that we've worked our way through a complete weight and balance problem using the computation method, let's do a few more weight and balance problems that you will likely find on the FAA written exam. Let's assume we're using a four-place airplane that has a maximum gross weight of 1,600 pounds. The empty weight is 1,104 pounds. The pilot weighs 155 pounds. The passenger weighs 114 pounds. Will carry 28 pounds of baggage, and the oil capacity is 6 quarts, which is included in the empty weight. Total fuel capacity with long-range tanks is 38 gallons, with 35 usable gallons. Using this data, determine if the airplane is within the maximum certified gross weight limit. List everything you put into the airplane and note the weight. Now, add these weights. And subtract them from the maximum gross weight of 1,600 pounds. As you can see, we're 11 pounds over the max gross weight of the airplane. Even an amount as small as 11 pounds can affect the weight and balance of the airplane's response in turbulent conditions. So let's eliminate some weight to bring the airplane within the gross weight limit of 1,600 pounds. In this case, you could remove 11 pounds of baggage from the baggage compartment, or another possibility would be to carry 2 gallons less fuel. In this next problem, here's an example of an incident you may run into many times while flying. During pre-flight, there are 8 quarts of oil in the engine. In this case, the oil weight is not included in the airplane's empty weight. The fuel tanks are filled to capacity of 38 gallons. The total weight of pilot and passengers is 670 pounds. The airplane's empty weight is 1,364 pounds, and a maximum gross weight is 2,300 pounds. How much baggage can you carry without exceeding the maximum certified gross weight of the airplane? List each item by weight and total these figures. 2,277 pounds is the answer. The next step would be to deduct 2,277 pounds from 2,300 pounds gross weight. The difference is 23 pounds. This 23 pounds is the weight of the baggage that can be safely put on this trip. Let's work another problem. Assume a four-place airplane with a maximum gross weight of 2,450 pounds. List everything you plan to load into the airplane by weight. Adding up these weights gives us a total of 2,060 pounds, well under the gross weight of 2,450 pounds. But what about the airplane's balance? Let's compute the center of gravity using the arm of each weight. From the pilot's operating handbook, we look up the arm and add it to our list of figures. Your worksheet should look like this. The next step is to determine the moment of each position. You will use the formula weight times arm equals moment. Your calculations should look like this. Add up the moment column of figures for a total moment of 227,320. To keep the computations simple, total moments are usually given in hundreds of pound-inches. Divide 227,320 by 100 for a moment of 2,273.2, rounded off to 2,273. The gross weight moment limits chart in the pilot's operating handbook establishes limits for the gross weight of 2,060 pounds to be the following: forward moment, 2,276, aft moment, 2,437. Our calculation should fall somewhere between these two numbers to be within limits. Our number, 2,273, is less than the forward 1,276, indicating that we've loaded this airplane so the center of gravity is forward of the limits. This is not a safe way to fly, so some adjustment of weight distribution will be necessary. This is a good indication of why airplane's center of gravity is not to be left to chance. Let's calculate one more weight and balance problem. First, let's assume that we're using the same four-place airplane that had a maximum takeoff weight of 2,450 pounds and a basic empty weight of 1,500 pounds. Keep in mind that these weights are found in your particular airplane's weight and balance papers and can vary from one airplane to another depending upon how each airplane is equipped. Assume you plan to load your airplane with two 180-pound front seat occupants, two 100-pound rear seat occupants, and 85 pounds of baggage. How much usable fuel can be loaded aboard with the maximum gross takeoff weight? Start by listing all the known weight items. Basic empty weight is 1,500 pounds. Fuel is the unknown quantity. Front seat occupants total 360 pounds. Rear seat occupants total 200 pounds. And the baggage weighs 85 pounds. Now, total these known weights. Then subtract this number from the maximum gross takeoff weight. Therefore, 305 pounds represents how much fuel you can load for this flight, given the other weight constraints. Remember that aviation fuel weighs 6 pounds per gallon. So to determine how many gallons of fuel you can load, divide 305 pounds by 6 pounds per gallon, and you get 0.8 gallons. Since total usable fuel capacity is 57.2 gallons, You don't have to top off the tanks, but you would distribute the total of 50.8 gallon load evenly between the fuel cells in each wing. Also, loaded under these conditions is the center of gravity within limits. Begin by consulting the pilot's operating handbook for this particular airplane to find each particular item's arm, and then use the formula weight times arm equals moment. Your worksheet should now look like this. We now have all the information needed to calculate the center of gravity. Divide the total moment number, 283,600, by the total weight number, 1,450, which places the center of gravity 115.76 inches from the datum. With this center of gravity location, the answer to our original question is yes. The center of gravity is within the forward limit of 114.5 inches and the aft limit of 118.3 inches. Let's assume for our next problem that full fuel is required, as well as 2 170-pound front seat occupants and 2 100-pound rear seat occupants. How much total baggage can be taken along on this flight? Remember, our airplane has a maximum gross takeoff weight of 2,450 pounds and a basic empty weight of 1,500 pounds. Begin with listing the items and weights on your worksheet. Basic empty weight is 1,500 pounds. 58 gallons of fuel weighs 340. The front seat occupants weigh 340 pounds. The rear seat occupants weigh 200 pounds. The baggage is an unknown value. Total the known weights. Subtract 2,388 pounds from the maximum gross takeoff weight of 2,450 pounds and get 62 pounds remaining for baggage. Next, we determine the center of gravity location. Consult the pilot's operating handbook to find the arm values for each particular item on your worksheet. Your worksheet should look like this. Now to complete the problem. Fill in the remainder of your worksheet using the formula weight times arm equals moment. It should look like this. Divide the total moment of 282,550 by the 2,450 pounds and get a center of gravity location of 115.3. Since this falls within the forward limit of 114.5 inches and the aft limit of 118.3 inches, the aircraft is correctly loaded. For our final weight and balance problem using the computation method, let's assume we're using the same airplane with its 2,450 pound gross takeoff weight and its 1,500 pound basic empty weight. This flight requires that we take along 4 persons weighing 170 pounds each and at least 38 gallons of fuel. So we begin by listing our items and their weights on our worksheet. It should look like this. Now total these weights to get 2,408 pounds. That's 42 pounds under the maximum gross takeoff weight of 2,450. Back to your worksheet, and let's once again use the formula weight times arm equals moment. It should now look like this. Now we have all the necessary information to determine the center of gravity location. Divide 278,036 by 2,408 and get 115.5 inches from the datum. This is within the forward center of gravity limit of 114.5 inches and the aft limit of 118.3 inches, so our airplane is safely loaded. On this program, we discuss some of the concepts of weight and balance and work out some theoretical and practical computations. Next time, we'll work some other weight and balance situations, graphs and tables. Before then, be sure to review these concepts in your textbook. See you then.
Last time we discussed the theories of weight and balance and the computation method of solving weight and balance problems. Let's pick up where we left off and learn how to use tables and graphs to solve weight and balance problems. The next method used to compute the airplane's weight and balance is called the tabular method. All the information and the solutions to the problems are found from tables in the pilot's operating handbook. For this problem, let's use the skipper that Jeannie and I have used for most of our lessons. If we refer to the pilot's operating handbook and weight and balance papers that are maintained and kept aboard the airplane, we will have no difficulty locating all the facts we need for the tabular approach to weight and balance. First, let's use this worksheet for recording our data. The airplane's basic empty weight and moment are taken from the weight and balance papers located inside the cockpit. To make your job even easier, all load moment tables in the skipper's pilot operating handbook, and for many other airplanes, give the moment divided by 100 so you don't have to work with such large numbers. These are called index numbers. The first values we'll fill in are the basic empty weight, which is 1,190 pounds, and a moment of 1,023. As you can see, since moments are provided in the pilot's operating handbook, you don't have to multiply the weight times the arm for each weight item. The left and right seat occupants' weight and moments are found on this chart page. Since the occupants table gives different moments depending upon whether the seats are in the forward or aft position, let's assume that both occupants sit halfway between the two extreme positions. Interpolate or split the difference between the moment index of 151 with the seat forward and 165 with the seat aft. The difference is 14, and since the seats will be in the middle, we divide 14 by 2 to get 7, which we add to the lower moment index, or a moment index of 158 for each occupant. So if the left occupant weighs 170 pounds, the moment is 158. The same is true for the right occupant. There is no baggage on this flight. Now add up the weight and moment columns. These subtotals are the zero fuel condition. The maximum ramp weight for the skipper is 1,680 pounds. This figure is found in the pilot's operating handbook under the weight limit section. By subtracting the total weight from the 1,680 pound figure, we see that there are 150 pounds available for fuel. How many gallons of fuel is this? Fuel weighs 6 pounds per gallon. The total weight is 150 pounds. Divide 150 pounds by 6 pounds per gallon, and we find that we can load aboard 25 gallons of fuel. 25 gallons is 4 gallons less than the full fuel load of 29 gallons. We add zero fuel condition and the fuel together for a ramp loading condition of 1,680 pounds and a moment index of 1,461. Now subtract the fuel for start, taxi, and run-up. Fuel for start, taxi, and run-up normally weighs 5 pounds with an average index moment of 4. Then, subtotal to find takeoff condition. Now assume you will burn 20 gallons or 120 pounds of fuel on your trip. The moment from the fuel table is 98. Both weight and moment are subtracted from the takeoff condition. This gives you the landing condition of 1,555 pounds, whose moment is 1,359. The zero fuel condition, the takeoff condition, and the landing condition moment must all be within the minimum and maximum moments shown on the moment limits versus weight graph or table for that weight. If the total moment is less than the minimum moment allowed, useful load items must be shifted aft or forward load items reduced. If the total moment is greater than the maximum moment allowed, useful load items must be shifted forward or aft load items reduced. If the quantity or location of load items is changed, the calculations must be reviewed and the moments rechecked.
To determine this, we now refer to the moment limit versus weight table, or we can use a moment versus weight graph. Let's use the table first. Locate the zero fuel weight condition of 1,530 pounds. The moment index, which is 1,339, must be within 1,304 and 1,360. At the takeoff condition of 1,675 pounds, the moment index, which is 1,457, must fall between 1,437 and 1,489. Again, we are within the allowable limits, since at the landing weight of 1,555, we must interpolate the moment limit to use the table. We choose to use the moment limits versus weight graph. Use this graph, which shows the center of gravity envelope for all combinations of weight and moments. Simply enter at the moment index of 1,359 on the left side. Follow the reference line until the moment line intersects the weight line equivalent to 1,555 pounds. Comfortably within the range again. It's very easy to see whether you're within the limits by using the center of gravity envelope graph. You can also use this graph to find the location of the center of gravity by proceeding vertically down from the intersection of the weight and moment lines. The center of gravity of the skipper loaded this way is 87.6 inches aft of the datum. With a new worksheet, let's try another weight and balance problem using the Skipper Pilot Operating Handbook and the tabular method. Assume the basic empty weight condition for our airplane of 1,190 pounds and a maximum takeoff weight of 1,675 pounds. Let's also say that full fuel tanks are required, as well as 50 pounds of baggage to be taken along. The pilot weighs 170 pounds and the seat is in the aft position. There isn't any passenger. Using the pilot's operating handbook, look up the moment index numbers for the different weight items and record them on your worksheet. Remember, with this method, multiplication of weight times arm isn't necessary since moment values are already computed and available in the pilot's operating handbook. Your worksheet should look like this. Now add these figures to get subtotals of zero fuel condition, 1,410 pounds, moment, 1,248. With full fuel tanks, fuel loading figures will look like this. Add the zero fuel condition and the fuel loading figures. The ramp weight should then read 1,584 pounds with a moment of 1,390. Subtract fuel for start, taxi, and run-up. This figure is usually 5 pounds with a moment of 4. Again, subtotal these numbers to find the takeoff condition. Let's assume that during this flight you will consume 20 gallons of fuel, which has a moment of 98 and a weight of 120 pounds. Enter these values on your worksheet next to less fuel to destination and subtract it from the takeoff condition values, which will give you a landing condition that will look like this. To determine if the airplane is loaded within the center of gravity limits, let's refer to the moment limits versus weight table. Locate the zero fuel condition weight, 1,410 pounds. The moment index of 1,248 must be within the minimum moment index of 1,198 and the maximum moment index of 1,253. For the ramp condition of 1,584 pounds, we must interpolate about halfway between the values of 1,580 and 1,590, or a minimum moment of 1,354 and a maximum moment of 1,409. 1,390 falls between these limits. With a takeoff condition of 1,579 pounds, we will use the moment values for 1,580 pounds to determine the minimum and maximum moment indices. Our moment index of 1,386 is between the minimum moment index of 1,350 and the maximum moment index of 1,405. For a landing condition weight of 1,459 pounds, use the 1,460 pound line to find limits of 1,241 to 1,298. 1,288, our moment index, falls between these limits. When a moments versus weight graph is available, you may prefer to use it when the weights are not in the increments shown on the table. Of course, if the moments are close to the limits, you'll want to be extra careful in your calculations. We'll show you how to use the moments versus weight graph later in the program. Just be aware that you can solve weight and balance problems using either the moment limits versus weight table or the moment versus weight graph. A weight and balance problem for a larger airplane using the table method could look like this. Let's assume a basic empty weight of 1,500 pounds and a moment divided by 100 of 1,650. The front seat occupants weigh 170 pounds each for 340 pounds and will sit with the seats in the aft position. The third and fourth seat occupants weigh 160 pounds each for a total of 320 pounds. There will be 45 pounds of baggage. We need to find the moments for these weights and subtotal both weights and moments for our zero fuel condition. The occupants table gives us moments for all people on board. The front seat occupants at 170 pounds each, with the seats in the aft position, have a moment of 190, or a total of 380. The rear seat occupants at 160 pounds each, on split seats, have a moment of 230 each, or a 460 total. The baggage table lists the moments for baggage. In this problem, it's 45 pounds, which is halfway between 40 pounds and 50 pounds. The moment is halfway between 67 or 75.5. The zero fuel subtotals read 2,205 pounds and 2,565.5 moment. Next, you add the usable fuel, which is 37 gallons. At 6 pounds per gallon, it weighs 222 pounds. And by consulting the fuel table, it has a moment of 259. The ramp condition figures read 2,427 pounds and 2,824.5 moment. The fuel for start, taxi, and takeoff is normally 5 pounds at an average moment of 6, giving us a takeoff condition of 2,422 pounds and 2,018.5 moment. Let's assume the trip will use 20 gallons or 120 pounds of fuel, which has a moment of 140. Subtract these from the takeoff condition to find the landing condition of 2,302 pounds and 2,678.5 moment. Last step is to determine whether the zero fuel, takeoff, and landing conditions are within the limits shown in the weight and moment table or graph. The table gives weight in 10-pound increments, with the maximum and minimum moment limits for each weight. The zero fuel weight of 2,205 is halfway between 2,200 and 2,210. So the minimum moment limit is halfway between 2,403 and 2,477, or 2,470. And the maximum moment is halfway between 2,603 and 2,614, or 2,608.5. It's easy to see that 2,565.5 falls within these limits. For the ramp weight of 2,427 pounds, we refer to the 2,430-pound line. The moment must be between 2,777 and 2,875. And 2,824.5 falls easily within these limits. To determine the moment limits of the takeoff weight of 2,422, refer to the 2,420-pound line. 2,818.5 again falls easily between 2,764 and 2,863. Last, for a landing condition of 2,302 pounds and 2,678.5 moment, refer to the 2,300-pound line, and the moment must fall between 2,599 and 2,721. Let's draw each of these load conditions on the graph, starting with the zero fuel condition. From our worksheet, we know that the zero fuel condition weight is 2,205 pounds, and its moment is 2,565.5. The gross weight moment limits graph has the moment values located along the horizontal axis, and the loaded airplane weight shown along the vertical axis. To use this graph, enter both known values on each axis. The airplane's weight of 2,205 pounds is on the vertical axis. The moment of 2,565.5 is on the horizontal axis. With your plotter or straight edge, draw a line across the graph through the envelope. Now, take your plotter and draw a line up from the moment number of 2,565.5 through the envelope. If the two lines intersect either on any of the envelope lines or anywhere inside the envelope, the weight and balance of the zero fuel condition is within the manufacturer's specified limits. Repeat the same procedure for the ramp condition. Find 2,427 pounds on the vertical axis. Then draw a line across the graph, intersecting the center of gravity envelope on the horizontal axis. Find the moment of 2,824.5. Draw a line up the graph through the center of the envelope. Do the two lines intersect on or inside the envelope? They do, and the ramp condition is within the manufacturer's specifications. The takeoff condition weight is 2,422 pounds. Its moment is 2,818.5. Find each number on the graph's axes. Draw the lines across and up the graph until they both intersect on or inside the center of gravity envelope. Finally, let's see if the landing condition is within the manufacturer's specified limits. Enter the graph at 2,302 pounds. Draw a line horizontally across the graph, intersecting the center of gravity envelope. On the loaded aircraft moment axis, enter at 2,678.5 and draw a line vertically up the graph, intersecting the envelope. As you can see, both lines intersect inside the center of gravity envelope, and the landing condition's weight and balance is within the manufacturer's specification.
The final weight and balance method we'll talk about is called the graph method, because it uses graphs to depict all values. Like the tabular method, we won't have to use the arms column or multiplication to arrive at our final value.
Basically, it involves the use of 4 pieces of paper, some of which are already familiar from earlier problems. The weight and balance data from your airplane, a worksheet that we can use to list our weight items, the loading graph, and the center of gravity moment envelope. The loading graph and the center of gravity envelope graphs contain all the weight and moment information, which is the reason this method is called the graph method. The loading graph has moment values along the horizontal axis, which in this example are divided by 1,000. The vertical axis shows weights. There are separate reference lines for pilot and front passenger, fuel, rear passengers, and baggage or child seat passengers. You will note that these values have been divided by 1,000 so that we can work with them easily.
Let's fill in the worksheet using the graph to see what our individual total values for weight and moment are for these conditions.
From the documents in the airplane, we obtain the empty weight and moment. Empty weight is 1,364 pounds, and the moment is 51.7 pound-inches. The 51.7 pound-inches is obtained from the airplane's current weight and balance records. Our pilot and front seat passengers together weigh 280 pounds. The rear passenger weighs 160 pounds. The baggage weighs 120 pounds. The 48 gallons of usable fuel weighs 288 pounds. And 8 quarts of oil weigh 15 pounds with a given moment of -0.2. We use the loading graph to obtain the other moment indices we need. For the pilot and front seat passenger, enter the graph at 280 pounds on the vertical axis. Then move horizontally to the pilot and front passenger line. Proceed vertically to the moment index of 10.4. Now enter this number on your worksheet. To find the rear passenger's moment, go back to the loading graph and enter at 160 pounds. Move horizontally across the chart to the rear passenger line. Then, vertically down again to the moment index of 11.7. Transfer this number to your worksheet. For the baggage weight, enter the graph at 120 pounds, moving horizontally to the baggage line. Then move vertically down to 11.4, the moment index. Add this to your worksheet as you did the other moments. With 288 of fuel, you have a moment index of 13.8. Enter this on your worksheet. Last, we have 8 quarts of oil, which weigh 15 pounds. The oil has a given moment of -0.2. Now total the weight. It should add up to 2,227 pounds. The total moment index is 98.8. Remember, the oil's moment is -0.2, so you subtract it. Once the worksheet has been completed, we're ready for the final step. For this, we need to refer to the center of gravity moment envelope. Our combination of total weight and moment should fall somewhere inside the design envelope. This graph uses a somewhat different format than the skipper's center of gravity envelope. Here we have total moments along the horizontal axis and total weight along the vertical axis. It simply means that we enter at both known values, weight on the left and moment on the bottom. Continue across and up the graph until the lines intersect. If the weight and balance lines intersect right on any of the lines or anywhere within the envelope, then the weight and balance is within the manufacturer's specified limits. The point where they intersect is our center of gravity. Is it inside the envelope? It sure is, and that means we are complying with the manufacturer's certification for both weight and balance.
On this program, we quickly covered the last 2 methods used to compute weight and balance for an airplane. Take the time to review and practice these methods in your textbook and viewer's guide. You'll see all 3 of these methods used on the FAA written exam. But most important, you'll want to compute weight and balance each time you fly to ensure a safe and legal flight. See you next time.